Okay, the following is a video about special right triangles, specifically 45, 45, 90 triangles and 30, 60, 90 triangles. What I'm going to do here is I'm going to do the same procedure for three different triangles. And what I'm going to do is find the missing side of each triangle and simplify my answer and kind of show you a pattern here. So let's do it for this first one. If I were to solve for this missing length x, I'd want to use the Pythagorean theorem. And let's just remember that if I label this side a and b and this side c, then we have the relationship that a squared plus b squared is equal to c squared. Okay, so if I plug 3 in for a and get 3 squared plus plug 3 in for b, get 3 squared, I'll get x squared. Okay, c is where x is. So I end up getting this. I end up getting 9 plus 9 is equal to x squared. And then I get that 18 is equal to x squared. Now, what I want to do here is I want to solve for x. And so since x is squared, I want to take the square root of both sides. And I end up getting this. I end up getting that x is equal to the square root of 18. Now, that's an exact answer, but we can simplify this, okay? I can split this up into the product of the square root of 9 times the square root of 2, okay? And I end up getting, I can take the square root of 9 and that gives me 3. So I get x is equal to 3 times the square root of 2. And that's an exact answer. And that is what I get here for x. I'm just going to write that here. 3 times the square root of 2. Okay, now what I notice about this triangle is that these sides are congruent. They're both 3. So then my base angles have to also be congruent. This is an isosceles right triangle. Okay, so let's move on to the next one. Okay, now I have something very similar here. Again, I have this length and this length are congruent, which means that these two base angles are congruent and it's a right triangle. So let's apply the Pythagorean theorem and solve for x. So if I take this, I'm going to take 8 squared plus 8 squared is equal to x squared. Okay, 8 squared gives me 64 plus 64 is equal to x squared. I end up combining those and I get 128 is equal to x squared. So now I have the same thing. I'm going to solve for x, take the square root of both sides. So I end up getting this. I end up getting x is equal to the square root of 128. Okay, now this is an exact answer, but I can simplify this. I can split this up into x equals the square root of 64 times the square root of 2. Now I can take the square root of 64 and I end up getting that x is equal to 8 times the square root of 2. Okay, and that's pretty powerful because that's kind of similar to what we just had. So I get 8 times the square root of 2. Now, in the previous example, if both of these sides were 3, then my hypotenuse is 3 times the square root of 2. So in here, 8 and 8, I get 8 root 2. So in this last one, well, if the pattern continues, because I have a 5 by 5 isosceles right triangle, if I solve for x, I'm kind of thinking I might get 5 times the square root of 2. So let's just see what we get here. Let's plug this into the Pythagorean theorem. I'm going to get 5 squared plus 5 squared is equal to x squared. So I get 25 plus 25 is equal to x squared. I get 50 equals x squared. I apply the square root to both sides, and I'm going to get x is equal to the square root of 50. Okay, well, can I simplify this? And the answer is yes. So if I take x, let me split this up into the square root of 25 times the square root of 2. And so I end up getting that x is equal to 5 times the square root of 2, which is what I had here. So this is pretty interesting, guys, and it means this, that in these right triangles, okay, all of these sides are congruent to each other, then my base angles are congruent. Okay, these two sides are congruent, so then my base angles are also congruent. Okay, and these sides are congruent, so my base angles are also congruent here. Now, what we need to see here, We have isosceles right triangles. So if these legs are both 3, then my hypotenuse is 3 root 2. If these legs are both 8, then my hypotenuse is 8 times the square root of 2. If these are my legs, then I get 5 times the square root of 2. Okay, so this is pretty interesting, and it leads us to a definition. And the definition is this. And I'm going to label this as these two segments are congruent. This is a right angle. These two angles are congruent. Now, because this is 90 degrees, okay, if I labeled both of these x and x, then I get that 2x plus 90 is equal to 180, all right? And so then I get 2x is equal to 90, and then I get that x is 45. So I know that each of these angles are 45 degrees, okay? So I'm going to label those as 45 degrees. So if I have a triangle like this, where I have a 45, 45, 90 triangle, which is just an isosceles right triangle, then it follows this pattern. And I could label this, usually what you'll see is that this segment is labeled L, and that this segment is labeled L. And then it kind of follows what we had, it's just that we're using a variable instead of numbers. But then I can say that my hypotenuse is L, that length, times the square root of 2. Okay, and this is the definition of a 45, 45, 90 right triangle. Okay, and we can use this, and we're going to use this a lot. You'll see this on the ACT exam a lot. You will see it once you get into Advanced Algebra 2 trig or trigonometry and even calculus. We use this relationship all the time. So it's a very, very powerful thing to know.